Okay, let's begin and welcome to the class again. So in the last class, just to recollect, we saw that the arithmetic mean that we are going to use in reality when we work with data is also a random process, right? So we saw that the arithmetic mean is a random process, and therefore we cannot work with arithmetic mean. The objective is to separate turbulence from the statistical mean, and therefore to study them. For that objective, we define what is called a true mean or an ensemble mean, which is only theoretically possible. We cannot have access to this, and that's because there are two conditions that is required. That is, samples must be statistically independent, and you need infinite number of samples. These two are not possible to get. Statistically independent events, that is, one event not influencing the other one, right? So this kind of statistical independence as well as infinite number of samples, both are not possible, and therefore it is only a theoretical definition. But we proceed with that, believing that this ensemble mean or a true mean exists, and therefore we can separate all the random components from the data. Okay, so we defined what is an ensemble mean, and then we also saw that the time mean or a time averaging is one interesting concept. People want to use it, but you have to be careful. This time mean becomes ensemble mean only when flows are stationary. Okay, if you have a flow like this where the mean is not a function of time, then this phi bar, over bar represents ensemble averaging, then this is fine in a stationary flow. But if we have a sinusoidal or an oscillatory flow, then the mean itself is changing with time. So in these cases, time averaging does not work. So in general, any type of flow, whether you take stationary flows, periodic flows or transient flows, ensemble mean works, and therefore we proceed with using ensemble mean. And we also saw that two signals can look very different but can have same mean. So the phi bar represents ensemble averaging. Phi is any random process, it could be your velocity, temperature, pressure. So these two are having same mean, but they look different. So the randomness has to be studied. For that, we define an higher order term called variance, right? So the variance can help us to know when two signals are having same mean here, right? And we also saw that when you ensemble average a fluctuation, x prime is the fluctuation component. When you ensemble average it, it actually becomes 0, because x prime can be split into or written it as x, which is the instantaneous signal itself, minus its mean, true mean. When you ensemble average one more time, then you get basically ensemble averaged value minus ensemble averaged value. So performing an ensemble average on an already a true mean does not change anything. It has already achieved its true mean state, so it has no effect, and therefore this should be 0. And when it comes to reality, because in lab or in simulations you do not have access to true mean, you are going to use arithmetic mean. There you must know that averaging the fluctuation will not be 0, some residue will be there. So smaller the residue, more closer it is going to 0 is good for you when you work in reality in the lab. Okay, so we defined also variance, which is can also be defined in terms of an RMS or a standard deviation. This has a physical meaning, I will come to that, what it means. And yeah, so I also discussed that you can get two signals with same mean phi bar as well as same variance phi prime over bar, like these two signals, let us say. But then one signal is biased towards the one side of the, it is having a greater excursion towards one side of the mean than the other compared to here, where it is more or less becoming flat. So for that, when two signals or two different data sets, two turbulence data having same mean, same variance, then we search for higher order terms. That is what I mentioned here. But the only thing is here, these two terms, the higher order terms, x prime cube over bar or x prime raised to the power of 4 over bar, we need such higher order terms, and I will explain what they physically, what is the physical meaning of this when I go to governing equations. And I did mention that this is related to skewness and flatness. Only to remember here is that this skewness and flatness are non-dimensional, they are non-dimensional. They are non-dimensional equivalents of these two. So we need to non-dimensionalize the third order and the fourth order term to get what is called a skewness and a flatness. Okay. So yesterday we look into all these parameters. One thing to notice is that when we look at fluctuations about the mean, we have already seen that ensemble averaging the fluctuation becomes 0. So I would like to graphically see how it looks like, that is x prime over bar is 0. So suppose if I have a signal, let us say I will take a bit complicated signal. Let us say I have a signal like this. This is the instantaneous component. Okay, let us call it x or phi or anything. Then this is the number of samples, of course, and then upon averaging I would achieve its mean. So this will be my true mean, x bar. So now what is phi minus? So if I want to represent phi prime, which is phi minus phi over bar, if I want this, how does that look like here? If I subtract the mean from these fluctuations, it essentially goes to this, correct? I am subtracting the mean, which is that red signal phi bar, from the black signal, which is the instantaneous raw data. When I do that, your fluctuations go, it will have excursions about 0, right? So mean of that, true mean of the signal is 0, right? And therefore phi prime is 0, right? We already saw the mathematical proof of it, but this is how it looks like. And therefore here in this particular signal, you should not do time average. If you do time average, then this phi prime over bar will not be 0. It will, you will have a sinusoidal signal also overlapping into it. So that's why ensemble average is the best in any class of flows. Okay. So this is one thing that I wanted to highlight. Another thing is, we also saw that the arithmetic mean is a random process. So if I am going to plot the arithmetic mean itself, okay, so let us say xn as n changes. So we had this throwing the dice game yesterday, where xn was changing 3.5, 4.1 and so on as n increases. Okay, even this is not a true mean, that we have already seen. So the value will go like this. So as n changes, so this is also a random process. So in practice, what should you do is the question. So the question you have to ask is, what to do in practice, not theory, right? So in a theoretically we have the ensemble mean, that is fine, but when you work with data that is coming from your simulations or experiments, what do you do in practice? We cannot get statistically independent data and we cannot get infinite number of samples. So first thing to check here is convergence. So as n increases, this xn should converge to x. X is the true mean or x bar. Okay. So increase n, that is the samples, to achieve convergence. convergence of arithmetic mean. Something like you have seen in the signal. It's no longer, so when it is coming to this part here, it is no longer varying so much. Minor variations is exhibiting. That's what some of you said. In the laboratory I took 7-8 samples and averaged, and it was not varying. In some other data you may take 7 million. Depends on what is your error tolerance here. But you should note that the ensemble mean of that fluctuation will still be not 0, some small value. Make sure it is small value. So that is the first thing. You have to increase n, take as many number of samples so that you achieve convergence. Okay. So then the other thing is, you cannot get statistically independent samples, but what you should do is you should check for samples that are not correlated. Okay. Samples or you can say uncorrelated. You have to collect uncorrelated samples. Okay. Collect uncorrelated samples. So what does this mean? Uncorrelated samples means, so physically let's say I have a pipe flow here. Okay. Pipe flow. I am only looking into a certain cross section. Okay. So here you would obviously see some turbulent eddies, some vortices. Such vortices are coming. So what you have to make sure here is that, let's say if you are taking data at a certain point, let's say I am taking data at this position. Okay. If I am taking a data at this certain XYZ location, and let's say the eddy is now sitting here. This particular eddy would have, let's say there is an eddy sitting around it. You must wait for a certain amount of time so that this eddy pass over it and then take the next sample. So this eddy should move out and be outside its region of influence. Then you collect the next sample at XYZ. So don't collect samples since you are going to do time averaging here, right? I am talking about in reality, not the theory. In reality, you are going to take continuous samples. Let's say in a wind tunnel or a pipe flow calculation, you are looking into, let's say, velocity at this position, continuously taking data. Don't do that. Wait for some amount of time so that this data is not correlated with each other. If you take data in the, which is, let's say, this eddy will, let's say it takes 10 seconds to move out of the zone of influence, then if you take samples every millisecond, all this data is influencing each other. You will not learn anything new out of that one. You wait for a certain amount of time. I will tell you how to compute this. There is a way to compute what we call an autocorrelation coefficient, the time required to wait in sampling. This experimentalists also do. This is all data collection and processing, right? So uncorrelated samples, and then check for convergence. Okay. So now we look into what is called single point statistics. Okay. Single point statistics. We kind of already saw this in this pipe flow example. So I am looking into data at a particular XYZ location and seeing recording the turbulence data. So in this single point statistics, let's say you are collecting data at a particular XYZ, at a particular XYZ location. When you do this, we have already seen the fluctuations about the mean, variance and so on. So this a special parameter appears here. Let's call it u prime over bar, v prime over bar, w prime over bar. Right, the three variances for UVW velocity component. This is called covariances. They vary together, right? So this is called covariances. And then you get the other t terms in the cross terms, or u prime v prime bar, u prime w prime over bar, and v prime w prime over bar. These are cross covariances, or simply cross correlation terms. Most popular is to use cross correlation, okay, or simply sometimes used as correlation terms, because you are looking into correlation of one velocity fluctuation, one random component with the other component, u prime with the v prime at a particular point, to see whether they are varying together or not. Okay, so this I already discussed. If these covariances are 0, you are essentially looking into a laminar flow. These are the random component that has to be there. In a turbulent flow, they are positive. Okay, it is squared, u prime square, right? So it is always positive. Okay, so these are always positive, the covariances. But the other ones, this can be positive, 0 or negative. 0, of course, that means it's not correlated. So these terms, it can be positive. Okay, positive implies that you have, let's say, both the components are varying together. One increases, the other one is also increases. Let's say u prime, example, if u prime increases, v prime also increases at the same point. At another xyz location, they may not be. Okay, it's different from position to position. So positive implying u prime increases, v prime also increases. So 0 implies no correlation. Both are not correlated at all. Negative implies you have, let's say, u prime increases, v prime decreases, an opposite trend. It could be v prime w prime also, or u prime w prime. I have just given an example here. And this will have a profound meaning when we go to turbulence, this correlation terms as well as the covariances. We use a different terminology when we go there. I will explain what it means.
So 0 does not mean that like u prime increases, v prime has to be constant. It can be random. So like in one instance it was increasing, in another instance it can also decrease. Like for a single point, it can increase or decrease or remain constant, but it does not have to mean that if u prime is increasing, it has to stay constant. Right?
They are basically exhibiting no correlation with each other.
Yeah.
Exactly same as, let's say, 0 in the covariance terms. So u prime v prime 0 is also not a good condition in the zone where correlation is not there. That is also indicates that there is no turbulence there. Okay. Yes, you can also do that. This is a single point statistics. We are looking into this u prime is a function of xyz time, and the v prime here is also the same location xyz and at the same time t. That's what we are looking into. Okay, and it's ensemble averaged. So this is, if I write it differently, so this is basically u prime of xyz t, v prime of xyz t. Okay, and of course his one question is that whether we can get correlation in time. This is useful in this pipe flow example I said, like how much time you have to wait. So you need to wait till the correlation has to go to 0. Okay, so before that let's define what is called a correlation coefficient. Okay, so let's define what is called a correlation coefficient. So let me call this as rho uv. If I am looking into the correlation of this, or let's say u prime v prime. So then this is defined as your correlation term, and it is normalized using its own RMS, which is u prime square average square root v prime square average square root, or you can write this as u prime v prime bar over URMS VRMS. So this value of course will take only value from 1 to minus 1. This is a correlation coefficient we are looking into. So this value will be minus correlation coefficient will go from positive correlation or anti-correlation. Now this is still at a single point statistics. If we do this in time, that is the question one student has asked, can we get correlation in time? Yes, this is useful to know how long I have to wait to get a new sample.